Okay, well, good morning, everyone. Thanks for
Thank you.
showing up. I'm Mark Santinello,
I'm Laura Caulfield.
and today we are here to tell you about some software that we wrote mostly to test SSDs that we call StorScore. Technical difficulties here. Hold on just a second. Why is my slide not advancing? Let's try again. Okay, here's the outline of what we're going to talk about today. So we're going to do a brief intro and explain who we are and why we put together this tool. And a lot of those motivations are going to be sort of the background section, which is different gotchas that you can run into when testing SSDs. And most of this stuff you'll see we account for in StorScore. And then Laura's going to take over and explain how the tool works. And lastly, we'll finish up, hopefully, if we have time, with a quick demo. And once again, my slide is not advancing.
Maybe we just do it in not present.
All right, maybe I'll just do it this way.
There we go.
Okay, I hope everyone can still see this. Okay, cool. So we are part of the CSI engineering team, Cloud Server Infrastructure team. So we come from a little bit of a unique perspective here inside of Microsoft. We're basically building servers that underlie our cloud services such as Bing, Azure, Office 365. And there's a picture there of our server. It's kind of a bare bones thing. It's cost optimized, and we deploy it at scale. One cool thing about our project is that we've contributed the design to the Open Compute project, and there's a URL there if you're curious. But as it relates to storage, Laura and I are really a big part of selecting which SSDs and HDDs we put into this server. And that's kind of the motivation behind StorScore. So we have some unique opportunities and some unique needs that make it a good idea, we think, to produce our own tool. So I'll just briefly talk about these. There are a lot of ways to do SSD and HDD testing that are not on a Windows platform, and we pretty much can't use those. We want to be able to tell our engineering groups relevant facts about the performance of drives in a Windows stack. Another thing that makes us a little bit unique is we have a wide variety of different workloads that we have to cater to. So you can think of what we call first-party services such as Bing, and we could go take an xperf trace and learn something about how they use storage. But we also have platforms such as Azure where the final customer can spin up a VM and do pretty much anything they like. So we really want to comprehend lots and lots of different workloads and do our best to select storage devices that are kind of universally good. The next sort of three bullets there kind of go together. We have sort of lots of different expertise at Microsoft. You know, you may not have thought that Microsoft had a server design team, but we do. And, you know, we also have all the OS folks and application folks. And so we really have a lot of flexibility to modify the stack based on what we learn. And, you know, you can even look at that as co-designing of the SSD and applications. And I think Laura has an example later on where you might find an opportunity, for example, to influence either the app or the SSD or both. And lastly, we have some maybe cloud-specific metrics, certainly metrics that are important to cloud. These are things like quality of service metrics, for example, for Bing. And some of those things we wouldn't get with the standard off-the-shelf tools. So in the server industry, there's this term AVL QCL, approved vendor list or qualified component list, and basically that's why we wrote StorScore. So I think you'll find if you download it and start playing with it that maybe it's not 100% perfect for what you need, but if you think about it in the context of what we wrote it for, it'll probably make a lot more sense. We have a task which is to survey broadly all the available SSDs that we might purchase and decide which ones make the cut. And so we needed a component level storage test that could help us build that QCL, that qualified component list. And as I mentioned before, we considered third-party services, outsourcing it, but there are some hiccups there. Often the results are not under Windows, or they're not in our server, the one server we really care about, but they're in some reference platform that we actually would never deploy. And we'd very much like to share our results, for example, with the SSD vendors to point out opportunities for them to improve and such. And as you can imagine, if we had purchased some testing report from a third-party entity, that you can't share that. We also found some deficiencies with the sort of standard tools. Everyone loves Iometer. It's really great for the GUI is awesome, and you can get an experiment running pretty quickly. But we needed something to do automated testing with. We kind of want to push a button and walk away. And Iometer, it can kind of figure out ways to automate it, but it's not really intended to be automated. We have some Microsoft-specific tests, and I think we might talk about this a little more later on when Laura shows you the recipes. But in general, there are some kind of oddball things we want to measure that are specific to experiences we've had operating cloud-scale services, and those things aren't provided by any off-the-shelf tooling. I already touched upon quality of service, but we want things like 5/9 percentile latency, which is important to Bing. And lastly, but probably most importantly, the methodology you use when testing SSDs is really critical. And if you get some things wrong, you can kind of confuse yourself. You can get results that aren't actually characteristic of the device. And tools such as Iometer, they were kind of written a long time ago in the hard drive era, and they're sort of really great for testing magnetic media, but they don't really. You can use them in ways that sort of get around the SSD gotchas, but they're not really intended to get around those. So you start kind of bending the tool into corners it doesn't want to go into. So with that, I'll segue right into these things. I apologize, if you're a real pro and have a lot of experience with SSDs, some of this stuff may seem like kind of SSD 101, but it's important to understand why we did what we did in StorScore. So the first thing is the so-called fresh out of the box condition for SSDs. And if you've read any review sites online, you've certainly seen this. This stems directly from the fact that SSDs are built around NAND flash. NAND flash has to be erased before it can be programmed. And when you get a brand new drive, it's of course all erased. But that's not the, operating condition. That's a very ephemeral condition. It'll only last for a few hours or days, and then the drive will be basically full. So you'd really like not to measure the drive in this unnatural state where it's mostly erased. Complicating this somewhat is the fact that SSDs, have so-called OP, over-provisioning. So for lots of reasons, there's actually more NAND in that little box than is actually exposed via the user visible LBA, logical block address space. And so really the right thing to do is to start all your testing before you take a single measurement. You want to initialize the whole drive by writing every bit of NAND in the box. And the way we do that is a little bit of overkill, but I think it's reasonable. We just write the whole drive twice. So StorScore will actually automatically detect an SSD, and as soon as it detects an SSD, it will initialize the whole drive twice with large block sequential. And typical drives have 7, or maybe for an enterprise drive, 28% OP. So, writing 200% of the drive will clearly cover all that. We've seen even one drive with 60% OP. That's pretty much the biggest one we've seen. So we immediately get out of the fresh out of the box state. Moving on to the next, even more trickier SSD gotcha, which is the so-called history effect. So this is something that maybe with the exception of these upcoming shingled magnetic drives, most magnetic media doesn't really have anything like this. So SSDs have this complicated sort of layer in the middle called the FTL, the flash translation layer. And it can get kind of fragmented up if you do things like random writes. It's not unlike old file systems 10 or 20 years ago that you used to have to defragment. And so there's this kind of surprising behavior that can occur with SSDs where if you run one workload for a while, then you switch to another, there's actually a transition phase, and that's what I'm trying to show with this chart here. It takes a while for the new workload to reach steady state. And really, you shouldn't measure that transition phase, because if you do measure that transition phase, well, what I should say is that transition phase is neither really characteristic of workload A or workload B. And that's really the gotcha. So the previous workload affects the current workload is another way to say it. And on a badly fragmented drive, that transition phase can actually take even hours. And I'll show you a quick, this is actual measurement from a drive that we had in the lab demonstrating this effect. So what you have here on the x-axis is basically time, and the y-axis we're just showing throughput. And this drive started off by being written to with small block of random writes. And then we began doing large 1 megabyte sequential writes to it. And what you can see is the performance tanks right away. And it's down there around 50 megabytes a second and sort of slowly creeping up over the course of 3.5 hours. And that's the first pass, right? This was I think a 480 gigabyte drive. And it took sort of 3.5 hours to write all of that again. But then immediately when you get to the second pass, it pops up there to well over 200 megabytes a second, and we get through the whole drive again in 30 minutes. That's an example of the drive sort of recovering from the badly fragmented state. Now this is a SATA drive, and it's kind of a client drive, and frankly it's kind of an old client drive. So we sort of chose this as an example of a really bad case to drive home the point. I wouldn't say this is characteristic of, certainly not of modern enterprise SSDs. But there is certainly a transition phase, especially between random and sequential patterns. And this is something that you really want to make sure you have factored out of your testing, or at least considered in your testing. So the way we deal with this in StorScore is we have this little utility we wrote called precondition.exe. Before we run this before we run the actual workload generator that captures performance metrics. And this thing is really simple. All it does is it runs the same workload that we're eventually going to run for the actual test, but all it does is monitor IOPS, and it basically does a rolling linear regression, fits a line, and waits for the slope of the line to be 0. And so the idea there is just basically once the slope is 0 and it hangs out at 0 for a while, the IOPS are flat, we're in steady state, and then we exit and continue on to the test. And Laura will go into the recipes a little bit later. You can tell StorScore to run tests in any order, but I think we've done something fairly clever in the default test matrix that we run. We're careful that we do all of the sequential tests before any random tests. And so the way to look at this is basically an optimization on time. Okay, so precondition.exe will get you into steady state, we think, very reliably. It's an effective firewall for the history effect. And so technically the tests should be atomic. We believe that they're atomic in the sense you could run them in any order, you should get the same result. However, if you did something like, say, run the random tests and the sequential test in alternation, you'd spend a lot more time driving to steady state, and your test matrix would take a lot longer. So we don't do that. What we do in our default test matrix is we're careful to run all of the sequential tests first, and then all the random tests second, And most critically, we really never transition from random to sequential, which is the most painful transition from the perspective of the SSD. And so very often we find that we spend maybe 10 minutes or 20 minutes driving to steady state, and then we run, an hour-long pattern for the actual test. So last little gotcha, there's a really popular controller out there made by SandForce that does this cool thing where it does compression on the fly. And I'm not aware of any hard drives that ever did this. So there's this potential gotcha where if you're using a sort of an older tool, Iometer is sort of famous for having different versions that have different behavior in this category. But basically, you've got some memory buffer in your tool that's going to be used as the source data for write tests, and what's in that memory buffer actually very much matters when testing an SSD controller that does on-the-fly compression. If you hand out a buffer full of zeros, you may get very, very, very fast performance, unrealistically fast. And on the other hand, if you had 100% entropy, if you filled your buffer from, say, a cryptographically sound random source, that might be kind of unrealistic in the other direction. That might be really pessimistic, and you'd get worse performance, and maybe that random pattern is not really characteristic of your actual data. So in StorScore, we try to be a little bit conservative. So by default, we actually do use the 100% entropy pure random data, but we also support different source data. There's all sorts of, I think we support 10% increments of compressible data. And so, just to show you how this matters, on the chart there on the right, that's using an SSD that's based around that SandForce controller. It's been in the industry for a while. And you can see there's a dramatic difference in random write throughput, just going from 0% compressible to 20%, and then all the way at the top there is 50%. So yeah, I guess with that, I'll now turn it over to Laura, who's going to tell you about how this thing works.
Cool. Thanks, Mark. So now that we're on the same page about SSDs, we'll dive into StorScore. So right off the bat, how do we actually get it starting? We have a concept called a recipe, and this allows us to actually feed it what kind of workloads we want to apply to the drive. So at its very simplest, here we have a recipe containing a single test. This is 8K random writes, or 8K random reads by the look of it. And this is the entire contents of one file that you can pass into StorScore. And then you just reference it on the command line when you call StorScore. And it's great because it reads exactly like English. This is something I would just write up on Mark's whiteboard, and it would tell us everything we need to know and nothing more. So this lets us run one test, but now we actually want to run a whole matrix of tests and walk away. This is one of the big powers of StorScore. We don't have to have a lot of engineering intervention in between tests. So this is an example of how we can do a whole matrix of tests. And again, this is something I would write on Mark's whiteboard. We just kind of list off all the parameters in each dimension, different access patterns, different write percentages we want to do. And so this defines a whole matrix of tests running each of the unique combinations here. And it also, this recipe showcases how we can include more complicated tests. Basically, if you can write it up in Perl, then you can put it into a StorScore recipe. So Mark can write up something that's pretty complicated, some kind of targeted test that I don't have to fully understand, but I can still put it in my test and run it on my SSD very easily. And then this piece down at the bottom shows an example of one of these more complicated tests. We've got a loop that runs smart commands over and over, and we can just execute that in the background and observe how our normal workload is running with that going on at the same time. So we've got the full functionality of Perl here behind our backs. We can also script these things really easily. You could sit down and imagine writing out a whole bunch of different recipes that you'd then execute very quickly. But this is really easy to generate a lot of data. Each one of these tests produces one file. So if we go and we do our 218 workloads that matrix defines, we run it on a bunch of different SSDs, then we come out with over 5,000 files. And maybe you can grep through for one or two parameters, see what everyone's throughput is, for a certain kind of workload, but it's really a lot to hold in your head or grep through. So that's why we have a parser part of StorScore as well. The first thing we do with the parser is take all these 5,000 files and boil them down into one spreadsheet. And this takes all the data in one format that you can see easily. And while we're doing that, we also look at the outliers of the drives. We highlight in green the good outliers, and we highlight in red the bad outliers. So we can see device A on this 30% mixed workload didn't do very well on the average latency compared to all the other devices on that workload for that metric. And we also put this in a format that it's easy to generate a pivot table and graphs. And if you're not familiar with pivot tables, I encourage you to get familiar with them. We'll see a bit more from Mark's demo in a little bit about how to do that. But this is really still too much data. We've got, I think, over 120,000 data points in this example. And so it's very important for us to be able to generate one score for each device. This is something we can take to our manager and say, okay, device A is going to score 72, device B is going to score 65, and so we want to choose device A. But it's also important that we take into account our different users. Bing, for example, would care about latency a lot more than Azure might. And so we need to understand those differences and include it in how we generate this score. So let's get into how we generate that score. The goal here is to enable a data-driven decision throughout the company. We want this really simple metric we can hand to anyone. And we do this by reducing to one score per drive. And we use a weighted average for each of the metrics for each of the workloads. So we take all of those data points in this block and we convert it into something called a z-score. Now, a little bit more background on what the z-score thing is. It's just a standard metric from statistics. Basically, for example, we can take drive A, workload X, and metric 0, and we take a distribution of all the drives on that workload and metric and identify where drive A falls in that distribution. And this represents drives A z-score for workload X and metric 0. And it gives us one piece of data that we can compare across all the different pieces of data. So for example, we wouldn't want to say that a bandwidth of 700 megabytes a second is worse than IOPS of 1,000. So the z-score gives us this nice comparable piece of data. It also gives us a couple things. Positive always means better, negative always means worse than the average. And also important to remember is that this is based on a cohort of drives. And this represents our decision-making process. Basically, at any time, we're going to look at all the drives that are on the market and say, this subset is the set that we want to actually purchase. So we've got these z-scores, but we still don't have our score. How do we actually combine them? This is where our policies come in defining the different needs of our users. So we've got maybe a Bing policy, maybe an Azure policy, and this is how we actually build them up into a z-score, or into a final drive score. We take each of the individual z-scores and we can apply weights to each of them such that, for example, we can give throughput metrics 50% weight, latency metrics another 50% weight to ultimately come up with this score. And we can apply multiple policies, so maybe we give throughput and latency metrics equal weight, but we also want to favor workloads that are mixed. So we can give a weight of 5 to workloads that are mixed and a weight of 1 to all the other pure workloads. And this, we can combine the two policies, and we can also use any kind of weighting system as long as we're consistent within each policy. This is a very powerful tool you can go in and modify easily to represent your users. But this is all driving at this final score. So once we do all of this math behind the scenes, then we can come out with a graph that looks like this. And this is really handy. You can put in front of a fairly technical manager or a non-technical manager, and right away some different things pop out. We can see that drive A is best in its class and that drive E and N are kind of straggling behind the others. But we can do more subtle things, like if we've been using drive L all along, then we can say, well, this cohort of drives A through I is going to perform comparable or better than what you've experienced in the past. But really my favorite here is if maybe you're looking at drive H, maybe this vendor has been really cooperative and they've got a really good price. So we'd really love to enable drive H as a drive that we want to use. Now we can delve into this data a little bit and decide how we can tweak our application or how we can have the vendor tweak their drive to improve its performance. Basically how we do that, we break it down into the different components that went into this weighted average of the score. And we can now say, well, it looks like the random mix isn't doing as well in the drive. So if the drive vendor is very motivated, we can have them improve their random mix. Or if the application developer is very driven to use this drive, we can direct them to favor a sequential mix over a random mix if they have that kind of control over their application. So this is a really powerful way to dive into the 120,000 data points to improve our technology. So this is kind of how we use StorScore. I'm going to do one final piece and delve into one of the metrics that we added through StorScore, and that is around SSD's main failure mechanism, the endurance. If you're not familiar with SSDs, basically the number of writes that you apply to these flash-based devices is limited. And so you can think of an SSD as a consumable. It can only have 2 drive writes per day and before it gets used up. So if you're a system designer, you're used to hearing things like drive writes per day or total drive writes, but really the real metric at play here is the number of writes that get applied to the NAND. And this is something called program array cycles or write array cycles. And this is the metric that we really need to measure and count. But the big difference here is that the controller introduces something called write amplification. And this can be anywhere from 1 in a good drive and workload, and we've seen all the way up to 20 or 30. So this is a really important system to be able to understand. We need to measure it for a lot of different workloads because it's workload dependent. It depends on the implementation that the vendor has put into their controller. So we'd really love to be able to measure it for each of the different workloads. Unfortunately, the metrics that have been available thus far are very, very slow. In the past, people really use the media wear indicator, and this is something largely for warranty to say, okay, well, the drive is at 99%, so it's about ready to die, and then your warranty is going to expire. And this metric is reported in units of 1%. So, for example, if we have a 1 terabyte drive that's rated for 30,000 program array cycles, you're going to have to write 300 terabytes of data before you see a single tick of this media wear indicator. And so for measuring just a single workload, we'd have to sit there and measure it on one drive, one dedicated drive, for almost 5 months before we get any information. So we worked closely with the vendors to expose some new telemetry from these drives called the controller writes. And this allows us to compute the write amplification factor for every workload in less than an hour. Well, once you get through the preconditioning phase, you can do this in 10 or 20 minutes. So we run our workloads for an hour, which means in this 5-month period, we can get the same kind of information for 17,000 workloads, or 1,700 workloads. So this is a really powerful metric to be able to expose, and it gives us some data like this. Well, it's going to be a lot of data, so let's introduce the graph first. We're going to show drive writes per day over 3 years, and we're going to show a wide variety of workloads here. We have different queue depths, different write access sizes, and different access patterns, random and sequential, and we'll show 5 different drives. And just to give you some grounding here, we usually have to get this information from the vendors, and they give us a really vague number that gives us a range from 3 to 14. So any of these workloads could be anywhere in there, but we don't have the fidelity until we have this metric. So after running StorScore on it, then we can get this amount of data, and it shows us some very interesting things. Not only does it give us confidence that this is actually what's happening, but it can allow us to identify some problem workloads. There's some variation here that we weren't too familiar with that now we are. And so we can direct application vendors to stay away from write access sizes that are 4K. But it also exposes things that the drive vendors aren't totally aware of. We've identified, well, you thought the write endurance would be high for very sequential workloads, but every once in a while there's maybe a drive that is doing something funny in the FTL that we weren't expecting. And we've actually already directed at least one drive vendor to go back and take a closer look, and they've fixed this problem. So this is pretty cool. We've been able to work better with both application developers and device developers to improve the technology and the way we use it with this tool. Now that we have kind of a rundown of how to use it and what we've added, I'm going to turn it back to Mark, and he'll do a demo of how to do it in person.
Cool. Thanks, Laura. So now I'm going to go ahead and run through how this thing actually works. At the end, there'll be a download link, so you can try this out for yourself. So really, the only thing you have to there's a slight echo. If you could mute. So really, the only parameter you have to give to StorScore is you have to at least tell us what target you want to test. There are sensible defaults, or what I think are sensible defaults, for everything else. So on this system, you can see I've got a couple of drives, and this one here happens to be an older SSD that I just kind of hammer on for testing purposes, so I'm going to use that one. But you can test a physical drive, in which case we'll disk part clean it and start fresh, or you can test an existing volume, in which case we'll create a test file in the available free space on that volume, or if you have your own test file, you can just target that. In this case, I'm just going to go ahead and write to this physical drive 4, and I'm going to use, I want to say it's an undocumented flag, but at this point in the project, they're virtually all undocumented. I'm going to use this quick test flag, which is really not intended for external use, really, because it's only really for us to test StorScore itself. It makes the test go pretty fast, though, so it's good for a demo. So the first thing you see here is StorScore gives you some information about what it's about to do and waits for you to say if you want to continue. It's detected that this target is in fact an SSD, which means it will do smart things. Like we talked about earlier, it'll initialize the drive by writing to it twice, and it will precondition the drive to steady state before each test. In fact, we might not see all of those things in this demo because quick tests turn some of them off, but you'll have to take my word for it. In this case, on my test system, I actually don't have, this is an external drive, it's in a cradle, so I get this warning telling me that I don't have SATA 3. And also because this is my desktop and Microsoft is very careful about virus stuff, it's complaining that I have a virus scanner that'll screw up my my latency measurements. All these things don't affect us. When we actually run for qualification, we use servers in the lab that are safely isolated. But so you get some nice warnings, and you also get sort of this little description here where it says, okay, I loaded this, what we call the turkey test, which is Laura's great name for the recipe that helps us to weed out the turkeys. This is a pretty long test. It takes, if you don't pass this quick test flag, as we're doing here for the demo, it takes about 2 weeks to gather all the data. And lastly, it warns you that you're going to destroy the drive. So when you press Y here and you destroy the drive, don't come crying us. Okay, so yeah, so I press Y, and StorScore is going to go through the motions here. He does a disk part clean. He's going to create a new partition and a new NTFS file system. We use NTFS by default. If you want to use ReFS or something else, you're welcome to create that ahead of time and just have StorScore target the existing volume. And then, yeah, we launch right into the very first precondition step. So what you see here is we're gathering some data so that we can begin to do that rolling linear regression. And we need a certain amount of data before we have enough to fit a line. Okay, now we fit a line and it's flat. And since it's flat, we dwell for a second to make sure it's not going to stop being flat. And once everything looks good, we continue to the first test. So, in actual application, this would take much longer, right? The precondition step would probably take at least 10 or 15 minutes, and you would likely run that step 2 for, we typically run it for about an hour, for each pattern. It's important to run each pattern for a really long time if you want to be able to say something sensible, for example, about these high percentile latencies. You know, for me to say something about 5 nines, I probably need to run millions of IOs. Yeah, and then so basically, you know, I don't want to sit here and wait for this, and I don't want to bore you with it, but this would go all the way through the test, and in the meanwhile here, it's writing results files for each one of these tests to the results directory. So at this point, I'm going to unceremoniously kill it and quickly show you.
This is the cooking show portion of the demo.
Yes, right.
The pie is baked. We're now pulling it out of the oven.
So in the results subdirectory, StorScore created this directory for this test, and it started anyway to fill it up with these files. For each test, we have a precondition. We pull some smart data before and after, and you can even open one of these. These are just text files that are the output from the actual I/O generator. These days, we use a nice piece of kit from the SQL team called SQL I/O. And you can see that this is basically human readable. You could go in here and learn something about this one pattern. But if we had let this test run for a while, you know, we would have hundreds and hundreds of files in here. So that's not really the best way. Really the right way to do it, especially if you're doing what we're doing and you're trying to qualify a large cohort of drives, is you want to run some kind of parser on it. So that gets us into the next phase, which is to run this little parse results script. What I'm going to do is I have a directory here called saved results, where I have a couple of drives that we measured previously. We put them through the whole 2-week test pass. And all I'll do is feed those directories to the parser, and I'll give it just this name foo for the name of the Excel spreadsheet I'd like it to create. And it goes through. There's a couple of warnings here we can just ignore. It does the whole scoring thing. It says it's going to detect some outliers, and then at the very end here, we're actually writing an Excel spreadsheet. And so I won't spend too much time on this spreadsheet because I have a better one that I'll flip to in a second, but the basic gist is, yeah, this is a giant pivot table. So let me actually close this one. And like Laura said, yeah, it's like any good cooking show. I baked the cake ahead of time. So here's a better example with a lot more devices in it.
I'm going to show them where the pivot table button is. So you basically take this chart and then you go up to the insert tab and then far left.
I'll totally do that.
Okay,
yeah.
Sorry.
So I think we're doing okay on time. So I'll just make a couple charts for you in real time here. So the first thing to see is that we've highlighted some outliers. You know, this drive here was really good in terms of max latency, but not so good in terms of some other metrics, which are in red. You know, if you scroll down far enough, you'll probably find a drive with a lot of green in it, which means it was, here you go, device D. Device D seems to have been a pretty good device. So you can learn some things just by looking at the raw data here. We also have this final scores tab. You know, Laura went into a lot of detail about this, what we think is pretty effective scoring policy that sort of enables us to not have to look at all those hundreds of thousands of data points on the first tab. And so, you know, we have these different policies, one that we think reflects how Bing would use a drive, and one that reflects Azure, and maybe one that's just more general. We can go in here and sort by these things and decide that maybe device D is the best device, and E and F are about the same, and maybe A, B, and C are sort of falling behind. And we also, you know, generally speaking, this might be enough to get a quick read, but you usually want to delve a little deeper. You know, we deal with a lot of vendors, and of course, if you were vendor A, B, or C, you might want to know why you got a bad score or a low score. So we have another large pivot table here that's basically a full accounting of all the components that went into that score computation. So yeah, let me show you real quickly how you can make a bunch of really cool charts without spending too much time. If you're an Excel wizard, this might be remedial. I'm slightly ashamed to say I learned this recently, and I think it's really powerful. So we do this all the time. We take all that data. In this case, I'm using that raw tab, and you just select it all and say you want to make a pivot chart. And then, you can very quickly create charts that are, just like the sort of thing you might get from a myometer. So what I'm going to do here is I'm going to say, all right, maybe just show me the right tests. We have some targeted tests that I'm just going to filter out because they're kind of noise for this example. Maybe I want to see access size, type, and queue depth. This is pretty common for the x-axis here. And generally this type of chart looks better as a line chart. And so let's say we wanted to look at megabytes per second. Bam, there you go. So this is a nice chart of throughput for these 6 devices versus a couple of different access patterns. This is all write throughput in this case. If I wanted to look at read throughput, it's easy as selecting this. I think you can tell by looking at these charts right away that this purple device, device D, is really awesome. It turns out that one is actually PCI Express and the other ones are SATA, which is probably a good time to mention that really it's incumbent upon you, the user, to compare drives that are comparable. Okay, we'll go ahead and create the bell curve and figure out z-scores, but if you give us drives that really are not comparable, that may not statistically make any sense. And in this case, it's probably not fair that we compare the SATA drive to the PCI drive, but it certainly makes for a more interesting chart. So that's sort of an easy example of kind of just a simple throughput chart. Let me show you something with scores. I'm going to do virtually the same operation where I'm going to go ahead and make a pivot table, but this time, or a pivot chart, but this time I'm going to make it from that score details tab. And I'll do something slightly differently here. I'm still going to filter out those targeted tests so they don't make the chart weird.
Like 10 minutes for questions.
Okay, maybe this will be the last one. Let's see. So I think we'll just look at the general score. And one thing you can see right now, let me maybe sort these so it looks like the chart that Laura showed you. So this might be the sort of manager slide, by device D is the executive summary. But you might also want to know a little bit more, and so one way we like to do this is we'll go ahead and turn this thing into a stacked column, and you can split this thing out by any one of these categories. So for example, I've just broken all these bars out by the write mix, so one here, 100% writes, 30% writes, or 100% reads, aka 0% writes is shown here in blue. It can be nice sometimes to add these little series lines. So you can see some, there's one interesting thing I think I'll point out here, which is that if you take a look at the relationship between device C and device A, there's something kind of odd here. A is winning overall, the bar is taller, but I think you can tell that this red area in A is actually smaller than the red area in C. So we have an example here where device A won, and yet device A is kind of not doing the best at these 70-30 read-write mix tests. So my feedback to the vendor of device A might be, hey, you should take a look at what happens to your drive when you mix reads and writes. Okay, I think given that we are pretty much out of time, I want to leave some opportunity for questions. So I think we'll stop there, and I'll just open it up for questions. Thanks everyone for attending.